Today, we're diving into the absolutely wild history of the computer, and this isn't just a story about inventions. It's a story about speed, just pure mind-blowing acceleration.
So really, how did we get here? I mean, how did we go from a machine that weighed 30 tons and filled an entire room to the supercomputer that you're probably holding in your hand right now? That's the crazy story we're going to unpack.
Okay, so to really get a feel for how fast things are now, we've got to go way back to a time when progress in calculation moved, well, at a snail's pace.
We're talking about things like the ancient abacus, all the way to Pascal's calculator, which was full of gears, and even Charles Babbage's incredible steam-powered analytical engine. I mean, these were genius inventions for their time, but innovation took centuries, not years. These were the mechanical marvels, but really, they were just the opening act.
And then electricity came along and just changed the entire game. This is where we get Generation 1 of the true electronic computers. And these things, they were absolute giants, all built around one piece of tech, the vacuum tube.
So, the vacuum tube was the big breakthrough. Just think of it like a light bulb, but one that can act as a switch, on or off. For the very first time, we could calculate with electrons instead of clunky physical gears. It was totally revolutionary, but, man, it came with some huge problems.
And yeah, this right here really paints the picture. The famous ENIAC computer was an absolute monster. It had 18,000 of these glass vacuum tubes. It weighed 30 tons, took up a whole room, guzzled enough electricity for a small town, and they were constantly burning out. So ENIAC proved electronic computing was possible, but it was nowhere near practical.
The fix for all those problems came from this tiny, tiny device that would, and I'm not exaggerating, completely change our world. Welcome to Generation 2, the age of the transistor, the tiny switch that changed everything.
So what was the big deal? Well, the transistor did the exact same job as a vacuum tube, but here's the key. It did it without a fragile glass bulb, without a glowing hot filament, without all that heat. It was solid, made from silicon, and that simple fact made it a total game changer.
I mean, this comparison really tells the whole story, doesn't it? The vacuum tube was big, breakable, hot, and super unreliable. The transistor, it was tiny, tough, cool, and incredibly reliable. Every single thing about it was a massive, massive improvement. This is what made smaller, faster, and way cheaper computers a real possibility.
Okay, so transistors were amazing, but now we had a new problem. You had to wire thousands of them together by hand. It was slow, frustrating, and super tedious. So the next great leap was figuring out how to build the transistors and their connections all at once. And that brings us to Generation 3, the chip.
And here it is, the integrated circuit. We just call it the chip. The brilliant idea here was, what if we could build not just one transistor, but an entire circuit, transistors, resistors, all the wiring on one tiny little slice of silicon?
And this was a total revolution in manufacturing. You could just forget about all that painstaking, error-filled hand wiring. All of a sudden, you could mass-produce really complex circuits, and that meant computers got even smaller, even more powerful, and way more affordable for everyone.
And that brings us to Generation 4, which is basically the era we're still in. The thinking went from a circuit on a chip to something even bigger. What if we could put the entire brain of the computer, the whole central processing unit, on a single chip? And the answer to that question was the microprocessor.
The microprocessor is the one piece of tech that unlocked everything we know today. The personal computer, your smartphone, your smartwatch, your car, pretty much everything. It's a whole computer on a single chip, and it's what kicked off the absolute explosion of technology we've seen ever since.
And the incredible pace of that explosion was famously predicted by this observation right here, Moore's Law. For decades, it was almost like clockwork. The number of transistors you could cram onto a chip would double about every 2 years. This law is the engine behind the great acceleration.
So let's just step back and put this all in perspective. You see the size shrink from a whole room to a closet to a desk, and now it fits right in your hand. But look at the speed. This wasn't a slow and steady climb. It was a straight-up explosion.
And this chart, wow, it really shows you the insane scale of that explosion. The jump from Gen 1 to Gen 2, that was big for sure. But the leap to Generation 4, it's almost hard to even wrap your head around. We are talking about 1,000,000 times increase in speed, and that number just keeps on going up. So, what's next? Well, Moore's Law is starting to hit its physical limits, and that means we're entering a really new, much less predictable era. We're right on the edge of the 5th generation, where the whole idea of what a computer even is starting to change all over again.
Yeah, these new frontiers aren't just about making faster chips anymore. We're talking about completely new ways of thinking about computing. Instead of just following instructions, we're building computers that can learn, almost like a human brain, with AI and machine learning. We're even tapping into the bizarre rules of quantum physics to solve problems that we used to think were literally impossible.
You know, when you look back, it's pretty clear. Each of those first 4 generations didn't just give us a faster machine. They completely reshaped our world. That whole journey, from the 30-ton giant to the supercomputer in your pocket, that's what built modern society as we know it. So the only real question left is, what kind of world will this next generation create?